Good afternoon, or whatever time of day it happens to be for you. This is a Math 1050 review of Chapter 6. The first thing we're going to do is solve a system of equations using row operations. And as a warning, some of these problems that we solve today will be a bit detailed, but they should have you good and ready for our next exam. So the first thing we do to solve a system of equation using row operations is to write our system of equations as an augmented matrix, which I'll do right below here. We put our coefficients of our terms x, y, and z. Our first row in this augmented matrix would be 2, 2, -1. Then we'll put a vertical bar representing the equal sign, and to the right of the equal sign, our first row has a -4. Second row, we will have 0, 3, -2, and 10. Third row, -1, -1, 1, and 7. Okay, so we're ready to start row reducing here. And I'm going to put a little template here for the order that we want to go in to get our matrix into row echelon form. The first thing we want is a 1 up in that first row, first column. Currently we have a 2 there, so to change that 2 into a 1, I'm going to multiply row 1. I'm going to get a new row 1 that is equal to 1/2 times my old row 1. So to do that, 2 times 1/2 is 1. 1/2 times -1, -1/2. And 1/2 times -4 would give us -2. The other rows here are going to stay the same for now. Okay, and we move on to the next thing we would want here is a 0 right below that first one in the second row. We already have a 0 here, so we're good. Following that 0 in the second row, we would like to get a 0 in the third row in that first column. So we want to change this -1 into a 0 somehow. So changing numbers into zeros generally involves multiplying another row and adding the multiple of that other row. And so we're going to get a new row 3 here. It looks like I can do something with row 1. In fact, a new row 3 would involve taking the old row 3 and adding to that, in this case, just 1 times the old row 1. Okay, so that's a fairly simple operation. I'm going to off to the side here, make some scribble paper, and I'm going to write down what row 3 currently is, -1, -1, 1, 7. I will add to that 1 times row 1. So 1 times row 1 would be 1, 1, -1/2, and -2. Let me fix that. That 7 kind of looks like 17 there, so let's fix that. Okay, so if we add these two rows together, we get 0, 0, 1/2, 5. This becomes our new row 3, so right now row 1 stays as it was. Row 2 stays as it was. Now our new row 3 is 0, 0, 1/2, 5. Okay, and we're going to move on to our next step, which would be to obtain a 1 in that second row, second column. Okay, so we need to turn this 3 into a 1. That's easy enough to do. Let's just get us a new row 2 that's equal to 1/3 times our current row 2. And now our matrix has row 1, 1, 1, -1/2, -2. Row 2 is now 0, multiplying through by 1/3. 0, 3 times 1/3 is 1. -2 times 1/3 is -2/3. And 10 times 1/3 is 10/3. Okay, our last row will stay the same as it currently is. I think I need to make this matrix a bit bigger here. Okay, so our third row would be 0, 0, 1/2, 5. Okay, so this matrix is moving along pretty nicely. We want to get a 0 now below the one that we just put into row 2. So our third row would have 2 zeros, and we already have 2 zeros here, so we don't need to work with our third row to get a 0 in the second position, but I do need to work with this 1/2 here to turn that 1/2 into a 1. I can do that simply through multiplication of row 3. So to get a new row 3 with a 1 in that third position, I'm just going to multiply the current entire row 3 by 2. And it looks like we're about done here. We have our row 1 is 1, 1, negative 1/2, negative 2. Row 2 is 0, 1, negative 2/3, 10/3. Row 3 is now multiplying through by 2, 0, 0, 1, 10. All right, and this is about as far as we can go in row reduction. Well, it's not as far as we could go. We could actually put this into reduced row echelon form that would make solving for the answer even a little bit simpler than what we're going to do. But having our matrix in this form of row echelon, what we call row echelon form, takes us to our next step. So we're going to just take this matrix here, move on to another slide, and we'll put the current matrix that we have right here. And now we're going to use this augmented matrix in row echelon form to solve for x, y, and z. The way we'll do that is we call this back substitution. We're going to start with this third row here. I'm going to write that third row as the equation that it represents, which would be z equals 10. And we've actually solved for z already. So we have z equals 10. Then I move up. I move up to row 2 here, which writing that as an equation would be y minus 2/3 z equals 10/3. I can plug in z equals 10 and have y minus 2/3 times 10 equals 10/3. Or y minus 20/3 equals 10/3. If I add 20/3 to both sides, I have y equals 30/3. And that's the same as saying y equals 10. So we have y equals 10. Okay, and now we move on to row 1 here, where we should be able to also obtain a value for x. So row 1 gives us x plus y minus 1/2 c equals negative 2. We plug in 10 for y. We plug in 10 for z. And we then have x plus 10 minus 1/2 times 10. 1/2 times 10 is 5. So we have x plus 10 minus 5, which would be x plus 5 equals negative 2. We subtract 5 from each side and get x equals negative 7. So we've now solved for x, y, and z. We can write our solution as the ordered triple, negative 7, 10, 10. All right, so this system is what we would call consistent because we do have at least one solution. Being that we have exactly one solution, we would refer to that solution as an independent solution. Okay, let's move on to our next problem, which is to write the system of equations corresponding to a matrix that we're given here. We want to identify the solutions and state whether the system is consistent. So we have a matrix with the first row 1, 0, negative 3, 2. If we write that first row as an equation, imagining that our variables here are x, y, and z, we'd have 1 times x plus 0 times y minus 3 times z equals 2. Our second row in this matrix is 0, 1, 0, negative 4, which would give us, for a second equation, 0x plus 1 times y plus 0 times z equals negative 4. Our third row, which is a row of all zeros, writing that as an equation, it would be the equation 0 equals 0. Okay, so it looks like we have some solutions going on here. The way that we would write those is I have y equals negative 4, so that one's good. As far as the first equation that we have here, x minus 3z equals 2, I'm going to solve for x and write x as being equal to 3z plus 2. And then we'll just let z represent our independent variable of sorts for our solution here. Our solution is going to be any ordered triple in which x is equal to 3z plus 2, y is equal to negative 4, and z is any real number. Okay, so we have a solution here. We actually have an infinite number of solutions, although not just any old solution would work here. For example, if z we set equal to 0, if we let z be equal to 0, then x would be 3 times 0 plus 2, or 2, and y would be negative 4. So there's only one solution to this system of equations in which z is equal to 0. So not any, we can't plug in 0, 0, 0 and have a solution. There are a limited number of solutions, but there are infinitely many limited solutions, I guess you could say. So what we would say here is this system is consistent because we do have at least one solution, but our solutions are what we call dependent. Dependent on what z is, if you think of it that way. All right, let's go on to another system of equations represented by a matrix, an augmented matrix. Our first row is 1, 0, negative 3, 2, which we could write as 1 times x minus 3 times z equals 2. Our second row in the matrix is 0, 1, 0, negative 4, which we could write as y equals negative 4. And then our last row, we have 0 equals 5 from the row which is 0, 0, 0, 5. Well, as soon as we see that 0 equals 5, that's never going to happen, right? So we would have to say that this system of equations is inconsistent. There's no solution. Okay, and we move on. Now we're going to use the matrices that were given. A equals the 2 by 2 matrix, 2, negative 1 in the first row, 0, 3 in the second row. And B equals the 2 by 2 matrix, 0, 4 in the first row, 5, negative 3 in the second row, to compute A squared minus 5B plus 2I sub 2. So we're computing A squared minus 5B plus 2I sub 2. And we'll write this out starting with a squared. So a squared just means a times a here. 2, negative 1, 0, 3 times 2, negative 1, 0, 3. And then we have minus 5b. I'm going to write that as plus a negative 5 times the matrix B, 0, 4, 5, negative 3. And then we have plus 2I sub 2. So you need to know here that I sub 2 is the identity matrix, the 2 by 2 identity matrix with 1, 0 in the first row, 0, 1 in the second row. And so we'll go through here and we'll start by multiplying the A matrix times the A matrix. We start with, we have a 2 by 2 matrix times a 2 by 2 matrix. The middle numbers match, which is good size-wise, meaning we can multiply these two matrices, and we end up with the 2 by 2 matrix, which we can tell from the outer numbers here. And so let's go ahead and do it. So we have this new matrix where we're going to start by taking row 1 times column 1, 2 times 2, which is 4, plus negative 1 times 0, which is 0. 4 plus 0 is 4. And then we move on and we take the first row in the first matrix times the second column in the second matrix. Okay, let me fix that real quickly. Okay, so we have 2 times -1, which would be -2, plus -1 times 3, which would be -3. So -2 plus -3 would give us -5. Okay, we move on down to the second row in the first matrix. And we're going to multiply that second row in the first matrix times the first column in the second matrix. So we have 0 times 2, which is 0, plus 3 times 0, which is 0. 0 plus 0 is 0. We move over to the second row in the second matrix. I'm sorry, the second column in the second matrix. So we're taking the second row in the first matrix times the second column in the second matrix. 0 times -1 is 0. Plus 3 times 3 is 9. 0 plus 9 is 9. Okay, now our next project here is to multiply -5 times the matrix 0, 4, 5, -3. We do that by just multiplying each number in our matrix by -5. So we have 0, -20 in the first row, -25, 15 in the second row. And we move on to multiply 2 times our identity matrix. 2 times 1 is 2, 2 times 0 is 0, and we end up with a 2 by 2 matrix, 2, 0 in the first row, 0, 2 in the second row. And now we're going to add the matching numbers in row 1, column 1. So 4 plus 0 plus 2 gives us 6. The first row, second column, -5 plus -20 gives us -25, plus 0 is still -25. The second row, first column, 0 plus a -25 plus 0, we get -25. And then row 2, column 2, 9 plus 15 gives us 24. 24 plus 2 is 26. All right, so we have our resulting matrix. 6, -25 in the first row, -25, -26 in the second row, or -25, +26 in the second row. Okay, and let's go on to number 5, where we're finding the inverse of a matrix. This is a bit of a long, involved project here. Usually we find inverses of 2 by 2 matrices, but I want to make sure you're good with finding inverses of 3 by 3 matrices. And this also gives us some more practice with row reduction. So let's go ahead and write the matrices we would need to here to find the inverse. So we write our matrix A to the left of on the left side of this augmented matrix that has the identity matrix to the right. Okay, so let's go for it. This time, instead of getting our matrix into row echelon form, we actually want to go a step further, and we're going to get our matrix into reduced row echelon form. And I'm going to walk through the ordering that we'd want to go with here. We start the same as we would start if we were getting our matrix into row echelon form only. We want a 1 in that first row, first column. Right now we have a -1 here, but I can actually swap rows because I notice that I have a 1 in that first position in the third row. So let's start by just swapping row 1 and row 2, row 1 and row 3. Okay, so if we swap row 1 and row 3, row 1 now becomes 1, 2, -1, 0, 0, 1. And row 2 stays the same, 0, 1, negative 1, 0, 1, 0. Row 3 now becomes our original row 1, negative 1, 0, negative 2, 1, 0, 0. Okay, so our ordering for reduced row echelon form, once we get a 1 in first row, first column, we want a 0 below that 1. We already have that, so that's good. And then we want another 0 below that 0 in the third row. So this starts the same as row echelon form. What we need to do next is we need to turn this negative 1 here into a 0. So when we're trying to get zeros, like the matrix we did a little bit ago, what we generally do is, in this case, we'll get a new row 3. We're going to add our current row 3 to some multiple of, in this case, it would be row 1. In fact, if I just multiply row 1 by the number 1, I'm good. Okay, so I want a new row 3 that's equal to my old row 3 plus 1 times row 1. Let's make some scratch paper over here. And I start by writing row 3, which is negative 1, 0, negative 2. 1, 0, 0. I add to that 1 times row 1, which is 1, 2, negative 1, 0, 0, 1. Adding those together, we get 0, 2, negative 3, 1, 0, 1. Okay, and so let's rewrite our matrix, leaving the first 2 rows as they are. And our third row now becomes 0, 2, negative 3, 1, 0, 1. Okay, we're going to move on, and the next thing we want to do in our order here for changing our matrix into reduced row echelon form is second row, second column, I want a 1. We already have a 1 in that position, so we're good. And the next task is to get a 0 right below that 1 where we currently have a 2. So I want to turn this 2 in the third row into a 0. I can do that by multiplying another row and adding it to this row. In fact, if we look here, we can get a new row 3 with a 0 in that second position that's equal to our old row 3 plus, let's see, I can add row 2 to that, and that won't mess up my 0 in the first position. But to add row 2 to row 3 and get that 2 to turn into a 0 there, we need to multiply row 2 by a negative 2. So I want row 3 plus a negative 2 times row 2. Okay, on our scribble paper here, we have row 3, which is 0, 2, negative 3, 1, 0, 1. We're going to add to that negative 2 times row 2, which would be 0 times negative 2 is 0. 1 times negative 2 is negative 2. Negative 1 times negative 2 is 2. 0 times negative 2 is 0. 1 times negative 2 is negative 2. 0 times negative 2 is 0. We add these two together, giving us 0, 0, negative 1, 1, negative 2, 1. And this becomes our new row 3. With the other 2 rows staying as they are. This takes a lot of writing, doesn't it? Okay, so our new row 3 is 0, 0, negative 1, 1, negative 2, 1. Okay, and let's see. The next thing I want now is in the third row, the third column, I want a 1. Okay, so far we're doing exactly what we did with row echelon form. And so that's easy enough here. I have a negative 1 currently in that position where I want a 1. So I just am going to get a new row 3 by taking negative 1 times my old row 3. And so there we have row 1 is the same, row 2 is the same, and now multiplying row 3 through by -1, I have 0, 0, 1, -1, 2, -1. Okay, and before we run out of space, I'm going to actually move to a new slide where I've written this current matrix as it is. So we're still finding the inverse of the matrix A, and this is where we've gotten to so far. We have our matrix in row echelon form, and we're going to need to work a little further then to get this into reduced row echelon form. So the order that we've gone so far is we have a 1 in the first row, first column with zeros below. We have a 1 in the second row, second column with a 0 below, and we have a 1 in the third row, the third column. Okay, so our next step then is to get a 0 in the second row, third column. So to do that, we currently have a -1 here, but if you look at this, I can just get this new row 2 that I'm aiming for by taking my old row 2 and adding to that 1 times row 3. Okay, so over here, some scribble paper. Let's take our current row 2, which is 0, 1, -1, 0, 1, 0. Let's add to that 1 times row 3, which would be 0, 0, 1, -1, 2, -1. We get 0, 1, 0, -1, 3, -1. Okay, so we have a new row 2. The other two rows stay the same, and we do more rewriting. So now our second row is 0, 1, 0, -1, 3, -1. Okay, and we're going to work now on row 1. Okay, so the next thing I want in row 1 is to turn this 2 into a 0. Okay, so to turn that 2 into a 0, let's see how we could do that. Well, look at row 2 is a nice candidate for that because there's a 0 in the first position, which won't mess with the 1 in row 1. There's a 1 in the second position, which I can easily multiply by, I can get a new row 1 by taking my old row 1 plus -2 times row 2. Okay, so let's over on our scribble paper, let's write row 1, 1, 2, -1, 0, 0, 1. Adding to that, -2 times row 2, which would be 0, -2, 0, 2, -6, 2. Okay, and we get 1, 0, -1, 2, -6, 3. All right, we're getting there. So row 1 now becomes 1, 0, -1, 0, 0, 1, 0, -1, 2, -6, 3. Okay, and row 2 and 3 stay the same. Sometimes this pen doesn't write quite right. Let's see, 0, 0, 1, -1, 2, -1. Okay, all right, so we have only one more number we need to mess with here. We need to get in the first row, we want a 0 in that third position. So let's see how we'll do that. So we want a new row 1 that's equal to, a nice candidate to help us with that is row 3. where we have zeros in the first two positions that won't mess with our current 1 and 0 there. So let's work with row 1. So let's work with row 1 by taking our old row 1 and adding to that. It looks like we can just take 1 times row 3. Well, that's kind of messy. Okay, so we want a new row 1 that's equal to our old row 1 plus 1 times row 3. And I need to extend the scribble paper a bit here. Okay, so we want to put row 1 here, 1, 0, negative 1, 2, negative 6, 3. We're adding that 1 times row 3, which is 0, 0, 1, negative 1, 2, negative 1. We get 1, 0, 0, 1, negative 4, 2. And I believe we're finished with getting our matrix into reduced row echelon form. So row 1 is now 1, 0, 0, 1, negative 4, 2. Second row 0, 1, 0, negative 1, 3, negative 1. 0, 0, 1, the third row, negative 1, 2, negative 1. And I'm going to double check this to make sure I haven't made any big errors before we go on to our next slide. So this matrix now is in reduced row echelon form. And because these problems take up so much space, I'm going to go ahead and move to our next slide, where we have the matrix as we just found it in reduced row echelon form. And all we want to do here is find the inverse of matrix A. Well, the inverse of matrix A is easy to find, because when we've converted our original form of this matrix with the augmented identity matrix to the right, now that we have the identity matrix on the left, the augmented part becomes A inverse here. So we can just write what we have here. A inverse is the matrix 1, negative 4, 2, negative 1, 3, negative 1, negative 1, 2, negative 1, and we're done. So this last step was the easiest part for sure. Let's go on then, and we're going to start working with solving systems of equations. This problem, it looks like a mess, all this writing that we have here, but basically we say the inverse of matrix A is A inverse is given to us. So the matrix A is 1, 0, negative 2, 2, negative 1, 3, 0, negative 1, 4. It's a 3 by 3 matrix. We're given the inverse of A. We're told it's 1/3 times the 3 by 3 matrix, negative 1, 2, negative 2, negative 8, 4, negative 7, negative 2, 1, negative 1. And we're going to use this inverse that we're given to solve the system of linear equations. X minus 2z equals 5. 2x minus y plus 3z equals 2, negative y plus 4z equals 7. Well, I'm going to start by writing the coefficient matrix that we get from the three equations here. Our coefficient matrix would be, in the first row of our matrix, we'd have 1 times x plus 0 times y minus 2 times z. The second row, we'd have 2 times x minus 1 times y plus 3 times z. The third row is 0x minus 1 times y plus 4 times z. And this coefficient matrix, notice, is the same as the matrix A that we're given here. So this is just our matrix A. And if you remember when we've been working on this in the past, the next thing we look for once we found our coefficient matrix is we find a variable matrix which has our variables x, y, and z in it for this problem. We usually give that variable matrix the name capital X. So this will be our capital X matrix. And then we also if you notice, if we take matrix A times matrix X, it's actually going to give us these three equations. You could try that. So our matrix A times our matrix X is going to actually equal our constant matrix here. So our constant matrix comes from the three constants here, which this is the matrix with 5 in the first row, 2 in the second row, 7 in the third row. And we usually call that B. So we have AX equals B. Okay, a true representation of our equations here. And if AX equals B, if you remember, we figured out, and we could work through this, but you can just refer back to some notes from class for this. We would solve the system of equations here using X equals A inverse times B. Okay, so to find X equals A inverse times B, we're given A inverse. So right here is A inverse. So our matrix X is going to equal 1/3 times the matrix -1, 2, -2, -8, 4, -7, -2, 1, -1. And so if we take A inverse times our matrix B, where our matrix B is 5, 2, 7, we will have solved for our variables. Okay, so let's start by ignoring the 1/3 for the moment, and we have a 3x3 matrix. We have a 3x3 matrix times a 3x1 matrix. We can multiply these two matrices because the middle numbers match. The number of columns in the first row, the number of columns in the first matrix is the same as the number of rows in the second matrix. We'll end up with a 3x1 matrix. And then instead of multiplying by 1/2 as I wrote, I need to fix that. We should be multiplying by 1/3 here. Okay, so let's see what we get. And matrix multiplication, just like we were doing before, we start by taking row 1 times column 1. Here we only have one column, right? So there's not really a choice. So -1 times 5 would give us -5, plus 2 times 2 is 4, plus -2 times 7, -14. We'd have what? -10 minus 5, -15 it looks like. And then we move on down, and we're going to take row 2 times our one and only column in the second matrix. So we have -8 times 5 plus 4 times 2 plus -7 times 7. And we get, that'd be -40 minus 41, -81. Okay, and now we take row 3 times our column. And so -2 times 5 plus 1 times 2 plus -1 times 7. What would that give us? That give us -10 minus 5, or -15. Okay, we're almost finished. Yay. We have 1/3 times -15 would give us -5. 1/3 times -81 would give us -27. 1/3 times -15, -5. So what have we found? We found our matrix X, which represents the variables X, Y, Z. We found X equals -5, Y equals -27, and Z equals -5. And we got it. All right. Moving on, we're finding the determinant of a matrix A here. Okay, so to find the determinant of the matrix A, we're going to start by choosing any row or column in here, and I will pick row number 1 to work with here. So I'm going to find the determinant of the matrix A by pivoting about the numbers in row 1. So let's start our determinant. We're going to start with the first position in that first row where we have a number 1. So we're going to take this number 1 times either plus or minus 1. If we sketch ourselves a little checkerboard matrix with pluses and minuses in the correct positions here, then we can see that this 1 in the first row, first column, is a position where we would have a positive 1. And so then we're going to multiply times the 2 by 2 determinant that we get by ignoring the row and the column with that 1 in it. That would give us the determinant of the little 2 by 2 matrix, -1, 3, -1, 4. And then we're going to move on to, in our second position in row 1, we have a 0. So we're going to have 0 times, notice this is in a negative position, so 0 times -1 times the determinant of the matrix we get by ignoring the row and column with that 0 in it. So we have the matrix 2, 0 in the first column, 3, 4 in the second column. Okay, and then we move on to the third number in that first row, which is a -2. So we have -2 times a +1 times the determinant of the 2 by 2 matrix, 2, -1 in the first row, 0, -1 in the second row. Okay, so remember to find the determinant of a 2 by 2 matrix. Say we have the 2 by 2 matrix A, B, C, D. We take A times D minus B times C. Okay, so let's go through and figure out. So for this first matrix here, we're going to have 1 times the determinant of the matrix -1, 3, -1, 4. We take -1 times 4 minus 3 times -1 plus, and this is why a lot of people like to choose a row or a column with zeros. 0 times anything is just going to be 0. So we'll throw a 0 there. And then we have plus -2 times the determinant of the matrix 2, -1, 0, -1. We take 2 times -1 minus -1 times 0. And let's just clean this up. So 1 time we have -4 plus 3 would be -1 plus 0 minus 2 times this determinant would be -2, -2. Okay, so what do we get? -1 plus 4 would give us the determinant of that matrix A here is equal to 3. All right, so we got it. Moving on, we're going to next use Cramer's rule to solve for y in this system of equations. So Cramer's rule actually uses determinants in its solution. And let's do it. The first thing we're going to note, though, is we've actually already found that the determinant that we found in our last problem was, if you look at right here, this matrix, or this system of equations, and if you write the coefficient matrix of the 3 equations, we have 1 times x plus 0y minus 2z, 2x minus 1y plus 3z, 0x minus 1y plus 4z. We actually have the coefficient matrix right here, and we call that matrix D. So we've already found our matrix D to solve this system of equations for y. And pay attention to this. If you have a 3x3 system of equations and you're asked to only solve for one variable using Cramer's rule, it's a good idea not to try to solve for all three because it is a bit of an involved process. But let's go ahead then and let's find, we found D. If I want to solve for y, y is going to equal d sub y over d, where d is the determinant of the matrix we get by replacing the y column in the coefficient matrix by the constants here to the right of the equal sign. So d sub y is going to be the determinant of the matrix that we get. We leave the x column the same as it is in the coefficient matrix, and we replace the y column when we're solving for y, d sub y. We replace the y column with the constants, 5, 2, 7. And then we leave the z column the same, negative 2, 3, 4. Okay, so this is our matrix d sub y. And as I mentioned in the last problem where we were finding the determinant d here, if we look for a row or column with a 0 in it, or maybe sometimes more than one 0, it is usually a little bit simpler to find determinants. So as you see, the first column here has a 0 in it. So let's go for that first column. So we're going to work with our first column in this problem. And to find the determinant using that first column, we will start by writing the 1 in the first position here. Remember our checkerboard of pluses and minuses. Okay, so this first one is in a plus position. Okay, so we're going to be multiplying our 1 by plus 1, positive 1. And then this is going to be times the determinant of the matrix we get by crossing out that row and column with the 1 in it. We have the determinant of the matrix 2, 3, 7, 4. Okay, and then we go plus. And we move on to the number in the first column, the second row. So now we're looking at the number 2 here. So we're going to have plus 2 times, that 2 is in a negative position. So we multiply 2 times negative 1 times the determinant of the matrix we get by ignoring the row and the column with that 2 in it, which would be 5, negative 2 in the first row, and 7, 4 in the second row. Okay, and now we move on down to the third row in that first column. So we're looking here at the 0, but you know, I can just write plus 0 because 0 times anything is going to be 0. So we'll simplify our lives here. So we're going to have 1 times the determinant of the matrix 2 times 4 minus 3 times 7. And then we're going to have minus 2 times the determinant of the matrix 5 times 4 minus negative 2 times 7. So we have 8 minus 21 minus 2 times 20 plus 14. So what do we get there? 8 minus 21 is negative 13 minus 2 times 34. So negative 13 minus 68 gives us the determinant. We're still finding d sub y. Took more writing than I thought it would here. So negative 81. Okay, so I found d sub y is equal to negative 81. And we already had d is equal to 3 here. So to solve for y is equal to y equals d sub y over d, which is negative 81 over 3. So we end up with y is equal to negative 27. All right, and you're welcome on your own. Go ahead and see if you can figure out what x and z are here. I don't think I have those written down, but it would be very good practice. And then you could check by solving the system of equations in a different way if you liked. There are 3 different ways that we solve system of equations with matrices. The first is by row reduction, by writing a system of equations in augmented matrix form and then using row reduction to put that matrix into row echelon form. The second way that we use matrices to solve systems of equations is to use an inverse matrix. And the third way is to solve a system of equations using Cramer's rule. Again, taking advantage of what we've learned about matrices in this chapter. Okay, so I think we've only got one more problem to do, and that is to find the partial fraction decomposition of 2x squared plus 5x minus 1 over x cubed plus 2x squared plus x. No lightweight problem, and I want to make sure you're really good with this. So we're going to go through all the steps. I'm going to start by factoring the denominator here. So if we have x cubed plus 2x squared plus x, we can factor an x out, making that x times x squared plus 2x plus 1. We can factor further as x times x plus 1 squared. Okay, and I'm not going to do any problems here where you would have an irreducible quadratic factor. So it might be a good idea to refer to your textbook for that. We're going to have all linear factors here. Okay, so what we can do then is we can take our system of equations. What am I talking about? Our one equation. We have one equation here, not a system. So we can take our one. Actually, we don't even have an equation. We have a rational expression. So we can take our rational expression. Sorry, it's been a long day, but we can take this rational expression, 2x squared plus 5x minus 1 over x cubed plus 2x squared plus x, and we can write this rational expression as 2x squared plus 5x minus 1 over x times x plus 1 squared. And I'm going to break up this rational expression into the sum of simpler rational expressions. So I'm going to write this as a over x plus b over x plus 1 plus c over x plus 1 squared. And refer to your textbook if you need some more help with this, or of course you can always ask me questions if you have a particular problem you need some help with. So what we do at this point is we want to, so right now we're kind of ignoring that first expression we were giving, and we're working with this that we have right here. And what I'm going to do is I'm going to multiply both sides of this equation by the least common denominator, which would be x times x plus 1 squared. I don't know if I have enough room to do as much as I'd like to with this, but we're going to take x times x plus 1 squared, multiply the left side by this expression, and so we're going to multiply 2x squared plus 5x minus 1 over x times x plus 1 squared. And then this is going to equal, to keep our equation, the same equation that we started with, we take x times x plus 1 squared, and we're going to multiply by, on the right side, a over x plus b over x plus 1 plus c over x plus 1 squared. Okay, we're basically getting rid of the fractions, if you can think of it that way. And so on the left-hand side, you can see that if we take x times x plus 1 squared over x times x plus 1 squared, that's the same as 1. So we'll write our left-hand side here as 2x squared plus 5x minus 1. On the right-hand side, then, think of distributing this x times x plus 1 squared through to the a over x. So we'll be able to we have x over x, which is the same as 1. We're left with a times x plus 1 squared. Okay, and then if we distribute through to the b over x plus 1, if I multiply x times x plus 1 squared times b over x plus 1, one of the x plus 1 squareds cancels out, so I'm left with b times x plus 1. Okay, and then I go on and I distribute through. If I had room to expand this all out, it would even be easier, I think, but it would take longer too. So then if we distribute, if I multiply x times x plus 1 squared times c over x plus 1 squared, x plus 1 squared over x plus 1 squared is 1. So we can just write this last expression as plus c times x. Okay, so we have what we need here to work with this. And I think because there's so much writing involved with these problems, I believe I made a new slide here where we take off from where we start, from where we left at the last slide. We start over here. So we had 2x squared plus 5x minus 1 equals a times x plus 1 squared plus bx times x plus 1 plus cx. This is exactly what we found from the last slide. And so what we want to do is we want to solve for a, b, and c. One way that we can solve for a, b, and c is by using what's referred to as the Heaviside method. With the Heaviside method, we pick values of x that will make some of these terms on the right side disappear. So for example, if I let x equal 0, then let's just write this whole equation, substituting in 0 for x. We'd have 2 times 0 squared plus 5 times 0 minus 1 equals a times 0 plus 1 squared plus b times 0 plus 1 plus c times 0. Okay, so you can see that both the b's and the c's, b times 0 plus 1 is 0. C times 0 is 0. So what I'm left with here is negative 1 equals a times 1, or a equals negative 1. Okay, I've solved for a. Life is good, right? I've got a equals negative 1. The next thing we're going to do, though, is we're going to go back to our original equation here, and I'm going to look for another number that I can plug in for x so that some other terms here disappear. There's some of the a's, b's, or c's disappear. Well, let's see. What if I let x be equal to negative 1? Negative 1 looks like a good number. X, negative 1 plus 1 is 0. Negative 1 plus 1 is 0. Let's let x equal negative 1. And let's write all the x's as negative 1 here. We'd have 2 times negative 1 squared plus 5 times negative 1 minus 1 equals a times negative 1 plus 1 squared plus b times negative 1 times negative 1 plus 1 plus c times negative 1. Okay, well, let's see what goes to 0 here. Negative 1 plus 1 is 0. And so a times 0, this whole term is going to go to 0. Negative 1 plus 1, again, 0. b times negative 1 times 0. We get 0 here as well. We're left with, on the left side, we have 2 times negative 1 squared would be 2 times 1, or 2, plus 5 times negative 1. We'd have minus 5, and then minus 1 equals c times negative 1. So what have we got? We've got negative 4 equals negative c, and that gives us c equals 4. All right, so we found A and we found C here. We're going to go on to another slide. I think we're ready for our next slide. So we have 2x squared plus 5x minus 1 equals a times x plus 1 squared plus bx times x plus 1 plus cx. And we've already found that a equals negative 1 and c equals 4. There are no other values for x that I can plug in and make things disappear, but I have a and I have c. So the next step here would be to choose any value I want to for x. Let's maybe let x equal 1 is a good number. If we let x equal 1, then I'm going to rewrite this whole equation, substituting 1 for x. I'd have 2 times 1 squared plus 5 times 1 minus 1 equals a. Oh, let's see. We know what a is, so I'm going to substitute in negative 1 for a. Okay, so I'm going to put negative 1 for a times x is 1, so 1 plus 1 squared plus, I'm trying to find b here, so I have b times x is 1 times 1 plus 1, and then plus c. Well, I know that c is 4, so plus 4 times x, which here x is 1. Okay, so let's see if we can get it. So we have 2 plus 5 minus 1 equals negative 1 times 2 would be negative 2 plus b times 1 times 2. So b times 2 plus 4. And so on the left side, we have 7 minus 1 would be 6 equals negative 2 plus 4 is 2. Plus 2b. So subtracting 2 from each side, I get 4 equals 2 times b, or b equals 2. Okay, so now we found a, b, and c. And, I have something else for b here, so I may have made a mistake. Let me backtrack here. So we have... So we're letting x be 1. So 2 times 1 squared plus 5 times 1 minus 1 equals a, which was negative 1, times 1 plus 1 squared plus b times 1 plus 1 plus 4, c is 4 times 1. So what do I get? I get 2 plus 5 minus 1 should be 7 minus 1 is 6 equals... And I have negative 1 times 2, that would be negative 2, plus b times 2 plus 4. Okay, so I'm not sure where I'm getting this wrong. So I have 6 equals 2b plus 4. Okay, well, I'm going to go with what I have here. It's not what I have in my notes, but hopefully this is correct. So we have 2b equals 4, b equals 2. And the next slide, I have b equals 3. Let me go back once more. So where I have something different here is, oh, okay, I found a mistake. I found my mistake, yay! Well, maybe that's good. I think it's good. Okay, so what I did here, if we take 1 plus 1 and square it, I don't get -2. I would get what? -4. So I guess it's good to work these out ahead of time, huh? So that would change this. And let's erase everything else there and kind of start from here. Okay. So we have -4 plus 2b plus 4. That would give us 6 equals 2 times b, and so b is going to equal 3. Good, that's what I was hoping to get, because I'd already moved it on to this next slide here, where b equals 3. So what we're doing is we're rewriting our original rational expression as the sum of 3 simplified rational expressions. And so what I can do then, knowing what a, b, and c are, is I can just rewrite this original rational expression as -1 over x plus 3 over x plus 1 plus 4 over x plus 1 squared. And we got it. All right, and I believe that's the last problem I was going to try for today. And so if you have any questions, please get hold of me. Again, our exam's coming up soon, so hopefully this will help you prepare for the exam. And have a good rest of your day.